Good morning to everyone who is joining from the United States, and good afternoon to those joining from Egypt. Thanks for participating. I'm very excited about this session on the topic of undergraduate heat transfer and plans for online deployment. We're fortunate today to have as the featured speaker Professor Tony Patera. He is the Ford Professor of Engineering and a professor of mechanical engineering at MIT. He does research in numerical analysis and computational science and engineering. Has earned many awards for that research and also for his teaching. He has previously served as the co-director of the Center for Computational Engineering, or now called the Center for Computational Science and Engineering, which runs graduate programs on these topics and organizes research on numerical methods and computational science, including design, optimization, modeling, learning from data, all very exciting topics. He has recently given a presentation to the Department of Mechanical Engineering on what he did during the spring when we were all suddenly disrupted by the COVID problem, and that prompted me to make this invitation. So he put together these slides and invited Max Kessler, who was in the course with him as a student and is now a graduate of MIT and working on the next phase of his career as a Fulbright scholar. So congratulations on that. So without further delay, let me introduce to you Professor Anthony Patera.
Thank you, Dan, and thank you for this invitation. I should just by a short bit of history related to Dan's introduction. The course I'm talking about today is a course that I offered in the usual fashion, traditional fashion, on the MIT campus last fall. That's fall of 2019. And it will be offered again in the fall of 2020. But early on in the pandemic, I made the decision and received approval for teaching the course online in 2020, quite independent of any global MIT decisions, because I thought it could be taught online and that could facilitate other courses which may need the on-campus territory. And so this talk is actually about the overall subject matter and pedagogical approach for this heat transfer subject, which I taught last fall. And I will also touch on the issues of how I will need to adapt that to the online format in the coming fall. This past spring, I was part of the pandemic disruption and the move from on-campus to online. I was not teaching this course. I was teaching a course on undergraduate finite element methods. And I will not be speaking on that today, except to say that it seemed to, in fact, proceed fairly well. But of course, the difference there is that subject matter is largely virtual, whereas heat transfer is a subject which requires eventually hands-on artifacts and experimental measurements. So I will say in advance that the part related specifically to the pandemic is towards the end of the presentation. And so I will maybe give a short wake-up call when I get to that part in the event that. All right, so let me know if anything does not transmit, either voice or video. So this talk, as I mentioned, is about undergraduate heat transfer education, and what I will call a postmodern approach, which I hope make clear momentarily, and with some discussion, of course, for plans for online deployment. And my co-conspirator today, as Dan introduced, is Max Kessler, working together this summer. Acknowledgements for some computations to my colleagues at the University of Illinois, to James Penn, a colleague who works on the experimental side with me at MIT, and as collaborators and participants, the students in my undergraduate heat transfer class during the fall of 2019, which in fact also includes, as you can see, Max Kessler. So first, an overview of the subject. The subject matter is macro-scale heat transfer. Because of other subjects in mechanical engineering, in my subject 251, I consider primarily external flows. And we discuss conduction, forced and natural convection. Today is on natural convection and radiation. And here's a short picture or cartoon of those three mechanisms: conduction in the solid, natural convection in the air, and radiation in the air. This is, you will hear often during this presentation about the 251, that's the subject number here, 251 project case studies. That's a central feature of the subject and one that requires online adaptation. And this particular picture actually derives from a student, Sam Austin, in 251 in the fall of 2019, who created his own Schlieren system from scratch and was able to visualize the natural convection boundary layer that we've been talking about in class. So macro scale heat transfer, conduction, natural convection, radiation, typically coupled, external flows, and the context in 251 is everyday life. The idea being that everyday life is in fact a good model for many technologies, either man-made or natural, if you like. I give an example here of some of these 251 project case studies to give you the sense of span, everything from cooking s'mores in a barbecue pit, to Coke can warming up, to the differences in wool and cotton socks. This is in fact Max Kessler's feet. Cookies, skillets, defrosting pans, bagels, dehumidifiers, energy efficient wall systems, glasses, thermoses, and potatoes. All right, and that's a small sample from the larger group of case studies, all from everyday life. And as you'll see, I chose everyday life because I think that students have a natural vested interest to find out what happens every day and to be able to interpret it in terms of more mathematical and engineering context. But it also has the nice feature, you see, that all of these, which are associated with an experimental component, these experiments can be conducted, of course, at home. And that was not the reason for my decision, but it turns out to be fortuitous given the online context in which we now find ourselves. All right, so that's the disciplinary focus. The philosophical focus is what I call a postmodern perspective. And so let me describe that briefly, and let me start. Much of this talk will be about back of the envelope estimates, which I will sometimes abbreviate in this BOTE fashion, with a definition from Wikipedia, which says a back of the envelope calculation is a rough calculation, typically jotted down on any available scrap of paper, such as an envelope. It is more than a guess, but less than an accurate calculation or mathematical proof. And the defining characteristic of back of the envelope calculations is the use of simplified assumptions. Now, let me modify that slightly. A simplified assumption is not quite right. It should either be simplifying assumptions or simplified models. All right, so I will edit that into simplified mathematical models. And then lastly, I would just like to point out that I would suspect that many of our current students have never used an envelope in their life, at least for the originally intended purpose, and may not have one handy. And so perhaps the 2020 version of the back of the envelope would be a rough calculation, typically programmed in a minimal instruction set on a single screen, within a single screen script. So a concise program in the same sense as a concise handwritten derivation. So that is the back of the envelope. And questions you might ponder, originally this said questions you might ponder in 2020, but we're all pondering questions we did not anticipate we would be pondering in 2020, right? So I will reserve that set of questions for 2020 and ponder these questions in 2019. The first is, why do we teach back of the envelope, succinct, transparent, fast methods of engineering still in 2020? And related, why do engineers practice back of the envelope calculations in tandem with large scale simulations still in 2020? And I would argue it's that the large-scale simulation really can only be trusted in tandem with back of the envelope calculations, and I'll go into that in more depth later. But this explains the adjective postmodern, which is in an era where we increasingly rely on computation and large-scale simulation and opaque techniques in some sense. I think we need to return and at least preserve the back of the envelope calculations, historically so important. They now serve a different role. They're not the primary predictive mechanism, but rather they're the voice of wisdom that sits behind these large-scale simulations. And so that's one of the emphases of this subject. Other questions? How should we interpret the envelope? I already discussed that, single screen script. How can we study back of the envelope engineering analysis through the lens of undergraduate education, such as 251? How can back of the envelope benefit without losing essential advantages from computational advances, which of course have been substantial? And lastly, why is it that we have performed back of the envelope estimates? I guess the term maybe originates back in Fermi's time, but why have we conducted back of the envelope estimates for so many years and never thought about whether this is actually an activity which is fundamentally human or can be viewed more formally as an algorithm or a framework? And that question will be addressed by Max towards the end of the talk. All right. And again, I've asked if any of you have questions at any time, please feel free to enter them via chat, and either Dan or Dina or Robert will stop me dead in my tracks if it needs immediate attention. All right, so heat transfer 101. Most of you are probably know as much or more than I do about heat transfer, but I thought to get, again, orientation relative to the postmodern perspective, I would talk a bit about heat transfer. So first problem statement. In 251, we follow what I call an APEO format, which is that you describe a problem in terms of the artifact, the process, the environment, and the output. So I will be discussing a particular large family of heat transfer problems known as dunking, all right? And for that, we have the artifact as a solid body. The process conditions, the body is at uniform temperature T initial and it's immersed in. The environment is a quiescent fluid at temperature T infinity and an enclosure at the same temperature. And we're interested in the temperature of the artifact as a function of position and time. So that is the problem statement. And let me show you a few experimental results, all drawn from 251 project case studies of dunking. The first is a cookie that is in the oven and that it is dunked in air. This is temperature as a function of time. This is the thermocouple rise time. This is the delay before the environment reaches the center, and this is exponential decay. Here's a problem. Another student, a bagel is dunked, if you like, in air after leaving the toaster oven. And here is the surface temperature. And the surface temperature, of course, you see the square root that you anticipate. And we notice that the surface temperature and the center temperature behave in different ways, which of course is a signal that the conduction problem is described by a partial differential equation, the heat equation. Now I mentioned that we consider not just conduction, but convection, natural convection, and radiation. So here's a third little example of the dunking problem from another case study in which students had two potatoes that had left the oven and then were dunked in the air, but one was wrapped in aluminum foil. Aluminum foil has a very low emissivity or emittance, which means that the radiation is poor. So if you look at the center temperature of the potato, which is foil wrapped, the decay in temperature is due to natural convection. So this is primarily natural convection. On the other hand, for the unwrapped potato, we also have radiation, and you can see the larger or more rapid decay associated with greater heat transfer from the surface. So this little picture from a 251 project case study illustrates the coupled conduction, natural convection, radiation phenomena that must be incorporated into even the simple problem of a hot potato cooling in a kitchen. So from a mathematical point of view, we have a solid fluid system. The solid will bear subscript S for its properties and for the temperature within the solid part of the domain. I assume that the solid is the artifact. The fluid, subscript F, properties, temperature in its part of the domain. And of course, we have the solid-fluid interface, which plays a key role. Coordinate system, nothing here except definition of gravity. Far field conditions, T infinity, initial conditions, and the output is the temperature of the solid as a function of space and time. So what are the governing equations? Well, they are formidable even these days. The equations are the incompressible or Boussinesque, is the coupling term with temperature, Navier-Stokes equations. The convection in the fluid, the heat equation, solid conduction. Then we have our far field and our initial conditions. And the key point here is this interface condition. And this interface condition says that the temperature must match, but also that the flux in the solid must match the sum of the flux into the fluid due to natural convection and the radiation terms. So that makes this a multi-scale problem in both space and time, typically three-dimensional. For the higher Rayleigh numbers, the non-dimensional form, of course, of the buoyancy, they require many hours on many thousands of processors, right? So, and that is not the worst of it. In fact, there are further complications for mass transfer where I would need to add an additional scalar and also, of course, phase change information related to the interface. This is a project case study by Max Kessler that in fact included simultaneous heat mass transfer in this tub humidifier. So in the modern era, one might say, let's just compute the solution and use the parallel supercomputer as necessary. So what are the issues there? Well, the first is the input procedure, which is in fact error-prone and indeed blunder-prone. Just preparing an earlier talk of this version earlier in the year, pre-pandemic, I asked a colleague, an engineering colleague, experienced for some simulation results, and the predictions disagreed by a factor of 10 from what I expected based on a back-of-the-envelope estimate. And the reason was, is that there was a file related to certain defaults which had a factor, a amplification factor, which had been set many months ago and was never revisited. And without the back-of-the-envelope estimate, that kind of error, which is quite common, can propagate all the way through to final decisions. And so the input procedure is error-prone. The cost is high, the response is slow, the parameter variation is limited. The computational procedures are increasingly opaque. A posteriori error estimation is often not adequate. And I should point out that even with the firepower of supercomputers and the extensive set of equations, that you still make fundamental approximations. We do not treat every nook and cranny in this cookie when we solve the problem. Right, and we're already making modeling assumptions. Yes. Hello?
Oh, may I interrupt you for a question of my own?
Yes, that's allowed.
So on your slide, you make a distinction between an error and a blunder. And I wonder if the central issue in the distinction is how obviously wrong it is or the magnitude of the impact.
It's actually kind of both, but you make a very good point, and I use this word intentionally. And most modern good software, in fact, does have some form of error estimation and also adaptivity. And as a result, although it may be costly and slow response and all the rest, as a result, most often the errors are in the form of blunders. In that it's not converging to an answer, but it's converging to a wrong answer, which might be very different from the intended answer, as in the example I gave, Dan. Does that make sense?
It does, yeah. I think it's an important distinction.
Well, it is, and the reason is that back-of-the-envelope estimates themselves are not that accurate. And so a back-of-the-envelope estimate could not dictate that you needed to refine your finite element mesh by one more level to get an accuracy of 10 to the minus 3. However, a back-of-the-envelope estimate could prevent these kinds of blunders where you're off by an order of magnitude. So these very fine errors, we do require sophisticated software. And I would say that during my career, I would say that in most cases, the problems arise because of blunders and answers that are way wrong, as opposed to just a little bit wrong. Other questions or comments? Thank you, Dan. Other questions or comments in that context? So simulation is valuable, but I would argue only in conjunction with a backseat driver, right, in the form of a back of the envelope estimate. So what do we hope of a back of the envelope estimate? We would like it to be succinct, transparent in inputs, assumptions, justifications, and procedures, fast in terms of the development of the estimate as well as the evaluation. And here is the tricky bit. It needs to be reliable. It may be blunder-free because it is so, in some sense, transparent, but we need to check that we have both sufficient and demonstrable accuracy in order to be able to accept the results for its purposes. What are the roles of back-of-the-envelope estimates? Well, historically, of course, it's all we had, and so it was important for conceptual design and optimization. But these days, we're repurposing these same techniques that served us so well over 50, 60, 100 years in this different context of blunder detection as a complement to full-scale simulation.
Can I jump in again?
Yes.
So we have a comment from Professor Adel El-Shabasi, and it's related to a potential risk of introducing a simplification in a course. So rather than going further, let me invite him to ask his question or make his comment.
Okay, I see Dr. El-Shabasi here on the screen, currently muted. So I guess you can unmute.
Can you unmute and offer some?
Oh, okay. I can't unmute. Okay, this is Dr. Adel El-Shabasi from Ain Shams University Faculty of Engineering. And I actually appreciate the simplification method of professor, but sometimes some student, I feel that by myself, and when we give some sample example and try to simplify the test or the subject, I don't know why some students consider that the course is not difficult to spend enough time to study, and they consider the course is not important. So this is one side of the problem relating to the effect of this simplification on the student understand that the importance of the subject.
Thank you. Yeah, and yeah, it's a very good comment. And I should say that I did not encounter that difficulty in my subject, but I think for maybe the following reason. When the students did their project case studies, they chose problems of interest to themselves. So I'm just going to get back to that list and then I'll flip forward again. So these are all problems that they chose that were of interest. And I did not simplify the problem for them. They needed to simplify the problem. And so I think in all of these problems, or at least many of them, are very difficult to simplify in a meaningful way. And we insisted that they take experimental data so that, as I'll say later, assessment is by Mother Nature, not by some solution key, all right, which requires them to go through formal steps. And so as a result, I found that the students were energized, I think, Max can correct me if I'm wrong, by the fact that these were problems of interest that were daunting to simplify, but that could yield results that were comparable to experimental measurements. Does that address your question? The key is that we don't do the simplifications. We try to teach and help the students learn how to make the simplifications on problems where they would like to know the answer.
Actually, I agree with your concept. The concept I might even I myself try to simplify the some subject of the material testing or the material structure and so on. So I myself use the same technique or the same approach. But my question about how to deal with that, I should address my question in another way. How to deal with the student if you feel that the student consider the course is not important?
Let me ask this, is it a required course?
How to deal with the student if you feel that some students consider when you the simplify or let them try to get some simple experiment or something like this, how to deal with the some student consider that they don't spend enough time to study the course. They don't spend or
I have to say, I have not encountered that phenomenon. But I know that it certainly could happen. I find that that requiring them to simplify means they have to have a deeper understanding of the phenomena and the mathematics than, in fact, to consider the set of equations, the conjugate heat transfer, which, in fact, and I don't say this in a derogatory fashion, that an applied mathematician could write down without engineering skills or background or physical experience. And so I find that the simplification is much more challenging, and I find at least that the students prefer that to a course which they feel focuses on say, the mathematics of solution, as opposed to the cognitive processes associated with simplification to be able to confirm simulations. One thing I might suggest you could do is to develop some examples in which people consider very sophisticated models, ostensibly, that in fact give wrong results for any number of the reasons that I indicated, and they might then begin to appreciate that they have a role to play related to simplification, which is a distinct cognitive process compared to, say, digital calculation. Max, could I ask you if you have any comments on this from the student perspective?
Yeah, no, I completely agree with what Professor Patera just said. I think putting simplification in context, especially during the pandemic, not so much myself, but I certainly had peers which said, oh, classes have become easier because of the recognition that people are going through different things at home and can't focus entirely on classes. And so kind of the simplification is a necessary part of adjusting to remote learning. I personally didn't find that true, and I think it's unique to the classes that students are in. But if we put simplification in context and recognize that just because classes are more lenient on what is expected or have to remove material for the purpose of fitting things in during the pandemic, I think keeping in mind that what we're learning is not the whole detailed picture, but it's what's most important. And especially in a class where there are experiments and opportunities to go further in one's own interests, then what we're really learning is what is out there, and that there is a lot more. So keeping that in mind, and there's always opportunity to dig deeper in what the students are interested in, and trying to always find a way to have the students pursue and follow projects that they do find interest in. Then I think that is a way to deal with maybe not being able to fit everything in that we would normally in a class, but at the same time giving students the context that there's so much more, and we're here for you to explore that if it interests you.
Thank you, Max. Any other comments or discussion items in that regard?
We can always come back to it later.
Okay. All right. So now that we're all a little bit uncertain about simplification, let me discuss simplification. All right. So what is the back of the envelope estimate? Well, it's based on 3 or 4, but I'm just going to discuss today 2 key simplifications. And I had a detailed slide here, but I realized from the when I discussed with Dean and Dan that most of you have some substantial heat transfer background. So I'm going to speed up since we've had a lot of good discussion. I want to leave time for more. So the first key simplification is that we replace the heat transfer due to natural convection to the air rather than the conjugate problem. We introduce a heat transfer coefficient. And that heat transfer coefficient is evaluated typically experimentally offline, and it can be performed ex situ by virtue of an isothermal wall assumption, which in fact is effectively exact in certain important limits and generally a good approximation. So that means that rather than a coupled fluid-solid problem, we have a conduction problem now with a boundary condition in a solid, and offline, the heat transfer coefficient is evaluated or is first developed in terms of a non-dimensional relationship between Nusselt, Rayleigh, and Prandtl, and students then have this archive of correlations that they can access for purposes of characterizing natural convection, and a similar result, but in fact much simpler, can be affected for the radiation due to a linearization of Stefan-Boltzmann. So from the user perspective, this simplification eliminates the conjugate heat transfer problem, replaces it with a heat equation, and the natural convection and the radiation appear as Robin boundary conditions through these coefficients. And the student then would need to decide what is the right shape family, cylinder, sphere, more general, and what is the right length scale by which to evaluate the heat transfer coefficient, and then what is the, say, linearization temperature required to calculate the radiation heat transfer coefficient. So this is a key simplification that reduces a multi-scale problem in space and time, 3-dimensional, to a much simpler heat equation. But the heat equation is still in a 3-dimensional domain, and so we'd like to simplify further. And so the second key simplification is geometry. This is a typical Nusselt number correlation that many of you have seen. So for geometry, you may remember when you studied heat transfer, the typical charts that are used. Well, let me introduce the slab geometry, a cylinder and a sphere, characterized in each case by some length scale L. And the geometry simplification says that we will consider a modified geometry, omega S prime, which is some mapping, not necessarily affine, of a slab, a cylinder, or a sphere with some characteristic length scale L. And of course, some of these are infinite in extent. This is doubly infinite, the slab, but that's equivalent to insulated boundary conditions. So in fact, the infinite dimensional approximation domain to a finite domain is reasonable in this context. So that's the canonical geometry. So now we have a conduction problem. And the conduction problem says, given the thermophysical properties, the heat transfer coefficient, and our approximate geometry, which is slab, cylinder, or sphere as dictated by gamma, we have a 1-dimensional heat equation where the natural convection and radiation shows up through this H bar. Now, this maybe gets back to Professor El Shabasi's point and also Max's comments about simplification, which is that this process right here, which in some sense corresponds to what we might think of as solution, is not the emphasis in 251 and is not the issue, in fact, more generally. This is a trivial problem in one space dimension that can be solved with rigorous a posteriori error estimates by, say, finite difference finite element methods. So the emphasis on the course is not simplifying for the students, but enabling the students to simplify. And that is a very challenging problem. And that is the cognition process that really goes into back of the envelope, is identifying the parameters. First, by analyzing the geometry and the process in the environment, what shape family and what length scale should we choose, and what linearization for the Stefan-Boltzmann to obtain a reasonable estimate for the heat transfer coefficient. Then we need to perform additional geometry analysis to determine the mapping, but in particular the slab, sphere, or cylinder, and length scale, which can accurately represent some more complex shape, like a bagel. or a potato. Now, finally, the last step is to put it all together and solve the conduction problem. But these days, that's really a push of a button. The cognition process that allows you to develop the model is the choice of parameters. And then finally, to make it more challenging, I often ask my students not just to develop a back-of-the-envelope estimate, but to develop a lower and upper bound by suitably choosing the parameters. For example, the linearization temperature for radiation. And through bounds, of course, implicitly, you develop an error estimate, right? And of course, these are not rigorous bounds, they're plausible bounds, but they do add quite a bit of confidence to the predictions. So that is, in fact, the back of the envelope, and it is a very difficult procedure. This geometry analysis, you can imagine, to decide and make all these decisions is considerable, and of course, it couples in with the parameters and heat transfer coefficients, and ultimately deciding on the proper regime, all right, for the solution. Any questions or comments at this point?
Don't see anything in the chat right now.
All right. So let me proceed. Dan, I think I need a little less than 10 minutes more, and then can we give max 10 minutes? That would put us a little over the original allocation, but accommodating for the questions. Will that be okay?
Perfect.
Okay. So implementation and deployment, traditional and online. So let me describe what I consider the 4 pedagogical elements of 251. The first is non-prescriptive problem statements, and this again gets back to why simplification is not easy. By the end of the subject, not the beginning, all of the problem statements and project case study suggestions are non-prescriptive. The problem is described in terms of artifact, environment, process, and output, in terms of natural language, in terms of pictures or photographs, or maybe a characteristic function, and numerical values with units as appropriate for data, with access to external information for properties and heat transfer coefficient. What is not permitted is guidance on how to solve the problem. All right, so that is not considered in the problem statement. So that in itself is not what our students are necessarily accustomed to, and now they need to apply back of the envelope analysis. But first, let me give an example of a non-prescriptive problem statement. You remove a bagel from a toaster oven, place it horizontally or vertically on a cooling rack in a kitchen at room temperature. In each orientation, how long will it take for the maximum temperature of the bagel to reach 45 degrees C? You pour your hot coffee just brewed in a double-walled aluminum thermos mug. How long will it take for your coffee to cool? Similarly, how long would it take iced coffee to warm? You stand in a quiescent room at 21 degrees C. How much energy do you lose, say in kilocalories, to the environment for minimal clothing, standard indoor clothing, and a Mylar parka? And in each case, estimate your skin temperature. We don't tell them how to do the problem. We tell them what the problem is. The second key component is mathematical modeling, and I emphasize that the students are really responsible for the back-of-the-envelope model as opposed to the estimate, which means that in addition there is a solution process, which, as I said, is really black box these days. And that means they have to analyze the geometry and process and environment and develop a heat transfer coefficient, again analyze the geometry to develop an idealized geometry such as a slab, and then finally provide all the complement or necessary inputs for the conduction problem. And if impossible, develop lower and upper bounds. A third key element of the subject is computation, and I'm going to skip this because it's probably not crucial. I use a large-scale parallel simulation Navier-Stokes solver in order to illustrate various features, like the difference in this conjugate heat transfer problem between the diffusion layer and the boundary layer. This is short time, this is long time. To illustrate how boundary layers apply to complex geometries, natural convection by a cylinder. And I actually confirmed by direct conjugate simulation that the back of the envelope heat transfer coefficient approximation is reasonably valid, and we highlight what the differences are. So that's computation. And then finally, assessment by Mother Nature. So when I first presented this, Dan, you may recall at one of the mechanical engineering meetings, I think people thought I was trying to get out of grading. And the idea was that somehow I had arranged a deal with Mother Nature, that she would grade the assignments and the project case studies. That would be nice, but that's not really what I have in mind. What I mean by assessment by Mother Nature is experimental validation, which is part of the course in many different aspects, including the project. Why? To develop intuition, to understand model assumptions, to confirm predictive power, teach humility, and build confidence, to reinforce the analysis goal, which is to predict nature versus anticipating the instructor's solution, and finally, to engender responsibility to appreciate the implications of flawed engineering analysis. So I believe that experimental validation is key. The main, it's not true it's the main assessment in points, but at least a half of the assessment is through a project. And so I'd like to discuss that and then the online implementation. So the overview is that the project theme is heat transfer in everyday life. The deliverable for each student is 3 case studies of their conception, which I always approach with some trepidation because students can have very challenging problems that even I do not know how to simplify appropriately. All right, but the students must choose these problems of interest to them. They must provide a problem statement, a mathematical model of the back of the envelope variety, we hope, with bounds and sensitivity, and of course, derivation and justification. They must predict the behavior for a particular instantiation and experimental validation. Now, in 2019, we had a reservation set up, and we had 4 or 5, maybe 6 E-Tech City cheapo laser grip IR barbecue thermometers, sufficiently accurate for our purposes, and one more accurate, more sophisticated, more rapidly responding thermocouple system. And all could be checked out by a reservation system. There's only one of these because it's more expensive. And then finally, I require interpretation, generalization, and perhaps design recommendation. So that's the project guidelines. I already showed you a sample of the projects just by way of relating to the current speakers. These are, as I mentioned, Max's feet. This was Max's humidifier. Where's the humidifier? Humidifier is not here, but this is the Trombe-Wall environmental system, another one of Max's project case studies. I include one here that came in after I made that picture because I just get back maybe to Dr. El-Shabasi's point about is simplification an indication of lower intellectual content, or is it a sign of higher intellectual content or larger intellectual challenge? And I think it's the second. And so here's an example from Megan McCandless, the student. Megan cooked pasta with friends. Here's the pasta. It's sitting in a Pyrex dish. So here's the pasta, here's the Pyrex dish. In a moment, it's going to be covered by this aluminum foil. And the question was, after, I think it was maybe something like 30 minutes or more, what is the temperature of the surface of the pasta? Now here is the kicker that I found particularly entertaining in this case. Megan made this pasta at a friend's house, put the aluminum foil on, carried it through the Cambridge winter night, got to her apartment, then measured the temperature at the surface of the pasta. Okay. And it turns out that it was good to within a degree centigrade. And to Megan's credit, she emphasized that she did not believe that this was entirely merited accuracy, and that had she had more time, and it would be imperative to perform a sensitivity study to understand to what extent that agreement was fortuitous, and how more generally for other instantiations of the pasta portage problem, what kind of accuracy you might expect. And that is what, in my mind, is the essence of simplification, is being able to understand very complex phenomena and to understand them in more detail than you would if you performed a full Navier-Stokes simulation. And so maybe, again, that addresses these comments. All right, so in fall of 2020, I will teach 251, and just a few minutes from the end, I'll turn it over to Max, in what I call the online plus context, or online plus format. So first, the online plus format, the general concept. A likely scenario for fall 2020 is that we will have some students on campus, and we'll have some students either not on campus or not in the classroom. Why? Ill, we very much hope not, or in self-quarantine, high risk or immunocompromised, international with visa or travel issues, are part of institutional low population density plans for campus use. So for that reason, I decided to structure the subject as online plus, The online is all necessary content, delivery, and assessment. So if, in fact, all students are off campus and everything is online, this would be the entire course. What is the plus? The plus is elective activities for on-campus students, but which will benefit all students, even those that are off campus. So the project guidelines for 2020 will be as follows. Students will work in groups. We will distribute any on-campus students evenly over the groups as much as possible. So hopefully each would have one on-campus student, if there are enough on-campus students. Each student, on campus or off campus, receives in the mail an eTech City IR thermometer. Actually, they're on back order, so it may be an alternative, inexpensive transducer, inexpensive enough that we can send them out to all students. The on-campus students will additionally have access to a shared single X-Tech thermocouple system, in particular for simultaneous measurement, for interior measurements, and for data logging. The data from the on-campus students and the off-campus students will be integrated into the case study. So let me take the example of the hot bagel half cooling. Each student in a group procures a bagel half instantiation. That means they go out and buy a bagel. Each student performs a validation experiment, the off-campus on single-point surface temperatures, the on-campus on multi-point interior temperatures. The students collectively develop a general theory that is applicable to any bagel instantiation. And then the students collectively compare the theory to experiment for their three, say, bagels, if there's 3 students in the group. And you can see that this group mechanism is more powerful than a single student because they can actually test the theory, in some sense, in parallel for different instantiations of bagels and collectively pooling their experimental results. So that is the plan for 2020 in order to maintain what I consider to be the key experimental validation aspect of this subject. So I am now going to turn it over to Max. This talk has been about back of the envelope and simplification and whether or not that's advisable and how it can be used. But I never really told you, how do we teach our students to develop back of the envelope estimates, right? And the question is, if we really feel we understand how to teach this material and what a back of the envelope estimate procedure should be, then we ought to be able to code up an algorithm, not for a particular problem, but to do back of the envelope analysis for general artifacts as we anticipate of our students. So Max and I have been working together on software, which is a first prototype denoted ARTI, which was originally for artificial students, but now is just ARTI. And Max is now going to tell us just a little bit about that software with a demo. Max?
Thank you. I'm going to share my screen. Can you see this okay?
We do.
So the idea of ARTI is a software that essentially performs the back of the envelope analysis, but it's a little more rigorous, a little more precise than something we might do by hand. And so what I'm going to do is kind of walk you through what we've been working on through an example. So Elijah Miller, in the same class as I took last year, did one of his case studies with a bagel, and he toasted them, cut it in half, and then on the left here in the horizontal orientation, he laid it down on a rack and used a temperature measurement to kind of track the cooling of the bagel over time. And he did the same with the other half of the bagel, only it was standing upright in a vertical orientation. And so for these different orientations, based off of some of the heat transfer models that we looked at in the class, we would expect different cooling rates. So as we kind of mentioned earlier in the lecture, the idea of a non-prescriptive problem in which not everything is given, but we kind of need to interpret a general problem statement and put it together in a way that is solvable and interpretable given the models that we use. We look at the artifact, the process, the environment, and the output. So the artifact in this case, which generally includes the geometry and the material, would look like, you know, the bagel and what is its material and what are those material properties. You know, other things could include, you know, the dimensions as I show over here, and, you know, the units that we're using to classify those dimensions and such. The process, which includes most simply just the initial temperature of the bagel before it's, you know, immersed in the air. So right as it's coming out of the toaster. The environment, most simply, is the, you know, environmental ambient temperature, so room temperature. And then the output is how we think about kind of what we're seeking to identify or to solve. So that could be, you know, temperature is a function of time as the bagel cools. So these different inputs over here in the top left are how we think of them broadly, but then we can implement those specific to this bagel case following kind of this structure that I have here in the bottom left. Now keep in mind, this software that we're working on is intended to be very general. So for any problem, we give it the information relating to the artifact, the process, the environment, and the output. And we tell it what sort of problem type this is. So in the bagel case, we're taking it out of the toaster and putting it in an ambient environment. So it's essentially a dunking problem. But the software would be just as capable as recognizing fin problems or wall problems, etc. But for this, I'm just focused on the dunking case. So after we kind of translate a real life scenario into this, you know, these artifact, process, environment, output language, then we can run this analysis. So I'm going to demo that now. So what you just saw is the same here. We tell, you know, the software what the artifact is, what the environment is, its air, this is its ambient temperature, this is the initial temperature of the bagel, and we want to know temperature as a function of time. So here I specify that because it's a vertical bagel, the direction of gravity points, you know, along one side of the bagel. So this would be in the Y direction, etc. So then what I can do is I create this instance in which it solves the dunking problem given all of this, and then we can look at the solution. So here what we see is a bunch of different graphs. So Artie doesn't tell the user right now what sort of approximation is the right one to use. It kind of just does all of it that a student might end up doing, and then it's up to the user or the student to interpret it and decide which is best. So this here is kind of a geometrical representation of the bagel. As you notice, it certainly simplifies the problem. It ignores that whole center hole. So again, it's up to us to evaluate whether that approximation is valid. Artie certainly thinks it is. And then it reports these graphs. So what I can do is, for that same thing, compare. I'm just replotting it here. I'm extracting the one plot that is relevant, which was surface temperature, using the model that we expect to use, that I would use if I was solving this by hand. And I've also plotted Elijah's, the student's data that he took, because he pointed the temperature probe at the bagel and measured it as it cooled. And so you can see there's quite good agreement between Artie's prediction and Elijah's data. So this is in the vertical case in which the bagel is upright. We can do the same in the horizontal case and see it's also quite good. So Artie offers other functionalities and flexibilities. So for example, if I want to look at how it interprets the problem, we can look at this plot. So what Artie has done is it takes an image of the bagel and identifies what is the bagel and what is not the bagel, and then gives it some depth. So this is the kind of the input geometry, but then as you saw earlier, Artie actually simplifies the bagel to just a disk. And so it determines that this hole is small enough that it's not necessary to consider it. Other things that might be relevant and Artie provides is, say we wanted to change the size of the bagel. So we could do something along the lines of so I'm making the bagel twice as tall. So if I replot this, you can see the software offers a lot of flexibility in quickly on the fly trying different geometries. We can scale the bagel to be larger, to be taller. This could be, both halves of the bagel. And so this is the sort of thing that, a student might be really interested in, because as we change things, we start to gather intuition on, what does changing something physical, like putting both halves of the bagel together, look like on the heat transfer level, and then we could replot it. But the thing is, if I was doing this by hand, it would take so much longer, and there's more opportunities for blunders or for errors on just the human side. So Artie is essentially what we're offering is the ability to solve these non-prescriptive problems. It can look up the physical or the Is that a
We
question?
mute? No, I think that
Okay,
that's
okay.
we can mute.
So it can look up the fluid or the solid properties of the bagel and bring those in. The dynamic solutions are the ability to on the fly change things like the geometry or things like the material. And one, as a recent student, I think that this sort of software could really help guide students learning heat transfer, because in one sense it is a black box. I'm asking it to do things, but I'm not seeing how it's doing it. And so certainly it can be a resource for checking my own work. If I did that bagel experiment, I could also write it out as I would solve it, but then verify with Artie. One last thing that it can do, though, which kind of makes it more than just a resource, is I can ask for its assumptions. So here, this is for the horizontal bagel. It gives me a report of some of the critical dimensions that were used. It tells me what the Rayleigh number was, so I can check, is this within the laminar regime, and is the model that I'm using accurate? What is the BO number, which kind of determines whether we can use like a lumped parameter model, or if we have to be using the more exact solutions. What are the heat transfer coefficients? And certainly, this report is something that we're continuing to expand so that it can include more and more. So the idea is this software can guide students as they're working along. And if they get stuck at one point in their solution of a problem, Artie can ask, you know, did you check the BO number? Did you check the Rayleigh number? Are you within these regimes in which the model you're using is accurate? And, you know, certainly because it's a software, we can do simulations. We could look at how you know, the temperature is changing with time, or how, you know, reverse it and say we want to know the temperature at a specific time, or the time at a specific temperature, and kind of solve the reverse problem. And then the other really important thing is that we want to make this package open access and transparent, so that, you know, anyone who has access to a computer can use this and benefit from this. So I guess the lasting question for you all is, what are other applications for a software like this? You know, especially in this unique time of a pandemic, how can Artie assist students across the world in learning heat transfer? How can it be a resource and, you know, kind of a model student, and help people who are remotely learning, who might be back on campus, but still benefit from something of this fashion? So I'll leave it like that, and ready for a discussion.
Thank you, Max.
Thank you very much, Max. Looking for hands up or questions in the chat. I'm going to pose a question myself, take the moderator's prerogative. Comment on the trade-off between a challenge that's posed using the everyday, like, you know, cooling a bagel, as opposed to something with more industrial impact, like quenching a forging.
Yeah, this actually came up Dan, in a discussion with one of the students that took it. It took an earlier version of this course, actually, 2051. Sorry, but I guess there are 2 points. The first is that from a heat transfer perspective, quenching or dunking, the modeling process is very similar. Now, of course, there are differences depending on the material and you know, if you have extreme temperatures and property variation. I realize there are differences, but the mathematical model ultimately, but also the simplification process is very similar in those two cases. And I actually had a student in one of my in the fall class who mentioned that in other classes sometimes he has technology examples, but that he's not going to ever be dealing with that particular technology, and that he doesn't have much sense of how it should behave. And he didn't say this, but also the point was he's not that interested in how it does behave because it doesn't relate to, right? And so I think the point is that if you can do a bagel, you can do an ingot, or an ingot with a hole in it or without a hole in it. And on the other hand, I believe you're more engaged. I mean, for example, some students took project case studies that involved their body temperature or their skin temperature when they were exercising. I mean, it's a question that naturally. And so I think it's just a better way to engage. I think it is representative. And we also are expanding everyday experience to include more life sciences. And so that is in some sense. And finally, because it does not involve typically advanced technology, all the artifacts are in your kitchen or in your bedroom or in your closet. It means that we can inexpensively do validation. And although I didn't anticipate that as being such an advantage, now that we're going online, it means that the course directly ports over because there aren't any demands on laboratory space, on high-end equipment, or on expensive artifacts. So on the other hand, I do realize one has to be careful not to trivialize. I mean, and especially during the time of the pandemic, you know, when we talk about how long does it take the bagel to cool, you know, one has to bear in mind that this is not saying that that should be the problem to which we should all be applying our efforts. What it's saying is that simplification in all contexts in a rational way for modeling the world around us is an extremely important skill, and that this is a way for us to exercise and develop those muscles.
Thank you.
Tony, I just want to add a comment to follow up on your comment. I think it's a very interesting way to think about also how to teach what we all think of as more of a traditional subject like heat transfer, and most mechanical engineering subjects at this point are considered traditional subjects. We all have to teach mechanics or thermodynamics, you know, mechanics or fluid mechanics or heat transfer, which are well established in their content, but how to think about teaching them in a different way so that students can relate to them better, both incorporating, you know, other tools, whether they're computational tools or modeling tools, or adding these hands-on experiments that make them a lot more relatable, make them a lot more also relevant, to be frank. So I think that kind of rethinking the way to teach these traditional subjects is a very important part of the message. And you know, where tools come in and where sort of, you know, evolving way of thinking about the world in terms of using tools is incorporated is a very important piece of this effort.
Thank you.
So maybe I would ask a question, since still the questions are being formulated. So Tony, have you thought of potentially an alternative experiment? I mean, I know you think a lot about different experiments to incorporate. So now we know the thermocouple and the cooking. Any other ideas being considered?
Well, Ahmed, I tell the students that they should choose something that has to do with everyday life. And actually, this gets back to your point as well, Dan, which is the following. So when I taught this subject, one student came in and he said he wanted to discuss his case study, which was the design of the casing for a rocket propellant. So I looked at him and I said, you know, the idea was this is supposed to be from everyday life. And he says, it is. I'm in the rocket club. He says, I launch rockets every day. And so what could I say, right? So and you know, and we have students that are involved in FSAE, right? That are every day they go in and they. So the point is that I don't exclude technology and I don't limit the students in scope. And what I find usually, Ahmed, is that although I anticipate that most things will happen maybe in the kitchen, that the students do branch out. And for example, many students were interested in human comfort and clothing, which required introducing the concept of a core to skin thermal resistance, which is something which also enters into wind chill. Other students were interested in those factors. So in fact, you know, I think, Ahmed, part of the problem with the way we teach these courses sometimes is that by choosing the problem ourselves, first of all, we choose a problem where we know there's an answer. And so in some sense, automatically it becomes a little less challenging for us and for the students. And the second is that we limit our scope to those things that either we're interested in or we have experience in. And so by opening it up so the students choose the projects, every year I get, well, I've only done this, well, actually I did 1.5 times, it was a mini project, but in this one occasion where I did it in earnest, I ended up with all sorts of projects which I would not have anticipated, either because they seemed too difficult or because it just was not within. I mean, for example, the s'mores example was a case where a barbecue pit, as s'mores, for those of you not familiar, is a strange American confection with marshmallows and chocolate. But right, so I would not have anticipated that. Another example is one of Max's cases was a TROM wall system, which is an environmental solar wall system. And Max had done the experiments in 2671 and now wanted to be able to develop a theory to predict those temperatures. So that gets us into the whole area of buildings, building systems, environmental. So I think part of the answer, Ahmed, is that this idea of choose your own problem is both dangerous for us, right, in the faculty, but what it really does is it makes sure that you're solving problems that are of interest. And I do think that over time, probably there will be more technology introduced, only because all of our students several students, for example, also chose new products that they were developing as part of 2009. So there were students that were developing lipstick dispensers and other, right? And so over time, I think it will expand. And I think the key there is to empower the students to be intellectually curious.
Yeah, I also find I learn a lot myself by asking the students to choose their own problems. I ran a similar experiment in the energy class, and I asked them to choose energy systems that are also relevant to them. And I learned a lot more from them than they learned from me in that aspect.
Well, I would agree with that. In fact, it's a little bit frightening, right? Because you're the usual model of instructor in charge it goes out the window. But I think that that's really part of the key of, as you say, these are classical subjects of keeping it fresh, and by their own interest, they're demonstrating that the material is still very relevant. And so I completely agree. Though I have to say that the heat transfer is a particularly nice subject for everyday experiences. Energy also is, but for example, in your other specialties, Ahmed, like combustion, it's a little bit trickier, right? To be able to get it in this particular form. So in that sense, heat transfer is, I think, a good first study for this kind of teaching, and then certain kinds of energy systems.
And just to jump in with a student perspective on kind of this method of teaching, I would say there's something very exciting and exhilarating about the fact that I can come up with a project idea and bring them to Professor Patera, and he doesn't know the answer. You know, it's not the same as an assignment in which I'm just trying to reach a solution that is known, but it feels novel, and that what I'm doing and what I'm bringing to the class is something that we can figure out together given the tools that you've learned throughout the course. And so, you know, I think having that ownership of a project is something that is really important for students, because it's unique, and it doesn't feel like you're doing something that's already been done. You're doing something new.
Yeah, thank you, Max. And on that point, I should also mention that you know, students choose a whole spectrum of projects from not so challenging but still interesting to very challenging. Max, in your particular case, all three of your projects, for one reason or another, were very challenging. And so I did discuss assessment and Mother Nature, but and that the point is to be able to predict nature, not to be able to tick off boxes. On the other hand, I just want to mention that when I do grade the projects, I'm looking at the process and the simplification process and the justification and the analysis and the interpretation and the recommendations. And that for more challenging, the error is of course increases with challenge, right? But the point is that's to be expected. And so, you know, a student that does a good job on a challenging project, even if the error, say, is a factor of 2 or 3 as opposed to 1 degree Celsius, right, would receive just as high a grade, or potentially even a higher grade, than a student that chose a less challenging project. So that again is to make sure that students don't feel like they should be looking for simple routes. And Max, in your case, all 3 were difficult, but so I think that earlier you asked about this question, does simplification indicate that the course is that the course itself is simple. And I think the answer is it can be done, so that's not the case.
So at this point, I'm not seeing hands raised, and I think it would be a good time to transition over to an Egyptian partner university view, if that's okay with everyone. So I'd like to hand it over to Professor Tamer Al-Nadi, who is Vice Dean for Education at Ain Shams University.
Hello, Professor Dan. Hello, Professor Patera. I really enjoyed the talk, and it gave me a lot of interesting ideas of how students can do things at home. And well, I guess students are always excited to do something that is related to their daily life. So every day in the morning, I guess most of people, they get use bagels for breakfast. So and then they heat it, and then maybe they go somewhere else and come back to the breakfast. So they need to know how long it will take until it is still good. So this is something, and the same applies for all the other examples as well. So yeah, I really enjoyed the talk, and it gave me a lot of inspirations of what to do with other courses as well, not only for heat transfer, but for other courses as well. I will do, I have a short presentation that I would like to show you. Can I share my screen?
Yes.
So do you see my screen now?
I see it.
Yeah.
Okay. So this is something different to what we have seen so far. And this is something that we have been doing at Ain Shams University for several years now, virtual experiments. So instead of bringing the experiment home to the student, we try, physically, we try to bring it home virtually. So in the last, I would say, 8 years, we started doing this. Maybe these numbers have become bigger now. About several virtual experiments for different domains. So I will take you through a quick tour through these virtual experiments to let you know what we have been doing, and to get some recommendations for what to be done in the near future. Of course, most of these experiments that we brought virtually are planned for more basic courses, basic chemistry, physics courses that are using some simple concepts. The purpose of these virtual experiments is not to enhance the practical skills of the students, but more to make him use of the procedures of the experiment. So, and at Ain Shams University, because we have a large number of students, usually, even if we are on campus, not all students do the experiment or have the possibility to do the experiment themselves. So in some cases, even the TA operates the machine, and they all look at it, they all collect readings, and then they write reports how to interpret these readings and so on. And in other cases, the students, they have groups of 5 students or so. One of them does the experiment, and the rest take, watch, and maybe it happens that they don't do anything by their hands at all. And of course, in few cases, they all students do it by themselves. And learn by doing. Of course, we all understand that doing something is very important. simplify complex information, try to minimize the burden of building new labs available virtually from anywhere 24/7, repeat an exercise. That's another thing. As I said, these are intended for basic courses that students need to repeat again and again in order to grasp the procedures and the basic information, the basic concepts. Of course, while we are doing this, we can safely add a row here and call it COVID-19, and you know, to treat with pandemics. Maybe later on we will have to deal with COVID-20. Well, you never know. So how it works? It starts with the what we call the subject matter expert. The subject matter expert is the teacher. He writes like what we call a storyboard, or it's like the scenario. He puts the process that the students need to see or do during the experiment. So this is one experiment about initial tension. So it helps the students understand and practice the initial tension that he has to introduce to specific bolts in order to withstand specific loads. So this is usually taught in basic courses in machine design. So this is how it looks in the beginning. The teacher draws with hand. I want to see this. I want to see this. I want to show the students this. And then this is how when it converts to a virtual experiment. So, for example, here the student sees the bolt and the junction, and when he tightens the torque, he can see what parts are in tension and what parts are in compression, and he can see this on the curves. And of course, he can play around. He can change the bolt size, bolt material, lower joint material, and upper joint material. So he can change everything. He can get the values directly based on his choices. He can experiment to calculate this to understand that he understands how to calculate these things and understand how to fix these things. Of course, this is just one screen from the experiment. Usually the experiment consists of multiple screens, let's say less than 10 screens usually. It's like the steps of the experiment. This is another experiment. I will show you several examples of different experiments. So this is another experiment of a signal analyzer. So usually the student is in the lab, and then he has an oscilloscope or a signal analyzer, and he have maybe actual signals that he is collecting and trying to do play around with the settings of the frequency analyzer in order to get different phenomena. So this is the Aliasing exercise, and he has a certain frequencies that he's measuring, and then he compares the sine wave frequency with the sampling frequency of the analyzer and see how this affects the reading. So this is the actual, this is the sampling frequency, and this is the sampling frequency 512, and this is a comparison. If he chooses higher sampling frequency, then he gets a better result. All this can be done at home. So all these are put on a website, and students can play around. Of course, there is accompanied with this experiment or virtual experiment, there is some kind of a lab sheet. So it's the same as if the student is going to a lab. The lab sheet tells him, okay, you need to do this, you need to do that. Okay, check the aliasing, check different sampling frequencies, and then he should write a report about it. And this is another view of the signal analysis, signal analyzer, and here it's digital modulation techniques. So we try to put knobs with the same view as a real frequency analyzer that he would see in the lab. We developed some other experiments for chemistry applications. So in chemistry, there are more difficult things because it's the equipment and the of some chemistry experiments are quite expensive, and students don't have access to it all the time. So it's good to bring them online. And also the some of these are dangerous. Some of these experiments are dangerous, and sometimes the chemicals themselves are expensive. So it's quite expensive to buy chemicals for all these numbers of students. So we had some a lot of chemistry experiments. This is an example of a micrometer. One of the things that students are exposed to in physics in the first year in college is how to read vernier calipers and micrometers. And usually it's not very straightforward, and he needs to exercise a lot. And maybe it's he doesn't have access to the lab to have a micrometer and tries a lot, and he needs to have someone beside him to correct him if he is reading correct or not. So this was an example that he has. There is a micrometer, and then there is a random generator of objects and a reading, and then he has to look at the reading and type in the reading here, and then it automatically corrects him if it's right or wrong. We also did some MATLAB emulator, because we at Ain-Shams University, we don't have licenses, students' licenses of MATLAB that we can give to all students, like at MIT. So, and sometimes we ask them to do some calculations in MATLAB. So this is like an interface. We are running MATLAB on our servers, and this is like an interface that student goes in and work with this environment as if he is working with MATLAB. And you can also run some simple M files. There are some other 3D simulation experiments for also mechanical design. There are lots of examples here from mechanical design, because this is what I mainly teach. There are lots of other experiments, of course, but in other domains. This was very beneficial for students in the beginning to see how things are connected together. And this is actually, he assembles it. So to start with, he has all these parts, and then he starts, okay, how to assemble things. We have large number of students, so it's hard to bring this physically into the lab or lecture and ask every student by himself to try to assemble them. And we did a lot of, some intelligence into this, so that it would allow the student to assemble things in the wrong order. So he can use a bolt in a wrong place as long as it is possible to insert it. And then he will discover this later in the assembly, that he needs to go back. And so we try to simulate a real life situation. Another experiment that we have is for materials, how to look at the atoms and the bonds between different in different materials. This is something now not completely virtual, but it is remote experiment. So we have this two-story building. It's quite, it's the height of it is about 1 meter. It's a two-story building, and there is an exciting motor on top of the building. So to simulate as if there is an HVAC chiller running on top of the building, and then it excites the different modes of this building or virtual building. And we have actually accelerometers that are mounted to this building, so the student can change the motor frequency and he's doing it at home, but the actual lab is on campus, and then he can change. Of course, this is done by reservation because not all students can enter at the same time. So a student goes in, changes the motor frequencies, and then look at the mode shapes of the building, and then he can compare it with calculations and interpret the results as well. This is another. This is a webcam looking at the actual experiment in the lab. This is another experiment, which is a vibration isolation. So this is just a simple isolator mass spring system. He measures the transmissibility and he calculates the transmissibility and look at the results. We've also developed some, it was a European project, so it involved several universities, Egyptian universities. So this was developed at the British University in Egypt, and they did, there was a professor there teaching a lot of courses in electronics. So this is an example for to prove or to demonstrate Faraday's law of induction. So this is a coil, and he changes the angle of the coil and see the effect of the induced voltage per frequency. So all these experiments actually and much more are available at this website, and it is open for everyone. So it doesn't, anyone can go and create an account and logs in and have a look at these experiments and run them actually. So we did a lot of physics and mechanical, civil, electrical experiments. These are several, you will find also several experiments for chemistry. We have recently also, but this is not for higher education, but this is for STEM education in schools. So we've developed some of these experiments for students in elementary schools. This is an example, of course, of the moon and sun eclipses. This was another interesting project we did in another European project with the Faculty of Pharmacy about toxicology. So this is like a virtual emergency room. They used it to teach their students who are in the emergency room, and then he gets a patient with poison somehow, and he has to do several tests, and based on these tests and analysis, then he decides to give a certain medicine. And of course, he can do this over and over again, and it is allowed here that he would give the wrong medicine and kills the patient. And then it's like game over, start from the beginning. So it was really helpful for them, and there is a lot of intelligence as well. So there are several poisons injected, and based on the analysis, so he looks at all the blood pressure, the eye, the lung, and looks at several things that from all these he decides on a certain medication. We did also some experiments in another project for students or children with special needs. So there were some designed experiments especially for them. Yeah, so that's about it. And yeah, I put here, I will share this presentation and all the websites you can go to and have a look at the experiments. We are actually using some of these physics experiments, especially physics. We've developed new physics experiments for this year, and it was very helpful with the COVID-19 situations that students could not go on campus, on lab campuses, on the campus labs and do these experiments. So it was good to show them these experiments at home, and they do it virtually. Any questions?
I see a hand up. It's been up for a while, actually. Thank
Yeah.
you for your patience. Adel El Shabasi, you can.
Yes, my question to Professor Tony, and he mentions that some student can take the course on campus and some student can take the course online. So can we consider that as a hybrid method of course learning? And the other question about if the student takes the course online, you're going to offer them the equipment or the experiment, what I mean, take experiment, I don't know, experiment kit to the necessary equipment or the necessary device to running the experiment. Thank you.
You're muted.
Yeah.
Muted.
Am I unmuted now? Yes. Which do you prefer? Well, I'll stay unmuted for you could call it hybrid. I prefer the online plus because it places the emphasis somewhat differently, which is that in the current context, I think we have to be prepared for a situation in which we only have online access and maybe even for all students. And so the Online Plus says that you take a course which is fully instrumented for online deployment. And then with the students that are on campus, you allow them additional activities, but that you design it in such a way that also the off-campus students will benefit. And in the case that I described, yes, the instrumentation required for the experiments, which would be a relatively cheap temperature transducer, either an IR barbecue thermometer, or I'm also now looking at a ThermoPen sort of high-end cooking thermocouple system. Those would be shipped to the students, and you know, maybe and with any other accompanying pieces that might be required, for example, tape if you're doing you know, worried about admittances. And so yes, that's the idea. If all students are online, then all students would be using just the less expensive diagnostic equipment, which in fact is perfectly adequate for our purposes, which is to determine if the model is roughly accurate. And if there are some students on campus, then we can enhance that to have better diagnostics and more information. Does that answer your question?
Yeah, that's okay. Thank you. Thank you.
I'm looking for hands, looking for questions.
Yes, yeah. No, thank you. That's okay. I was muted. So okay. Thank you. Thank you, Professor Ton.
Yes, thank you.
So if I can do a follow-up, so I infer from your statements before, Tony, that you believe that if you have at least some students on campus, in addition to students online, it's actually a better experience for everyone.
That is the goal, right? I mean, and like most sort of statements like that, the question is whether or not it can be realized. But I think but that is the goal, and the way I was hoping to achieve that is by making sure that all the students have some firsthand experimental validation experience, but that each will be able to give according to their abilities, as it were, online or offline, and that all should benefit. And I do think that in some of these experiments, there are different outputs of interest related to, say, the surface or the interior, and even if it's the same outputs, having, you know, these higher frequency, for example, or better response time equipment could supplement. So yes, that is I also had thought a bit about doing demonstrations, and the students would all do demonstrations, and the students that are on campus could video demonstrations that use this higher end diagnostic equipment. But that is the goal, Dan. What I do not quite understand yet is how the selection process will be made for online versus on campus, and whether it will be by class, but I don't think it could be, and whether I'll end up with therefore a mix, or whether it'll be a more homogeneous group. But the key point is that really we got caught flat-footed this past semester, and none of us, you in Cairo or we in Cambridge, were prepared. And so it seems much better to have a teaching plan where you are prepared for the worst case scenario, and you also have options that you can elect to engage that would give you more capability without much additional cost. So that is the philosophy. And in fact, I mean, the kinds of experiments that Professor El-Nadi described are all other ways in which, I mean, that the students that are only online can benefit from experiments, but you could easily see extending the idea, as you mentioned in your preamble, Professor El-Nadi, about the fact that the on-campus students could play some role in actually managing or somehow interacting with the physical apparatus that the online students are seeing only remotely.
So I think that the insight is an important one, but not obvious really, because Krishna Rajagopal, who is our Dean of Digital Learning, I think that's his title, he had told me and the committee apart, which deals with our academic regulations during the disruption, that he felt that based on the research, MIT faculty would be advised or should be advised that most of the data tells us that either all online or all in person are the preferred modes, and that hybrids are very difficult to implement with good quality.
Well, that's good for me to know before I attempt it. But I would have one question for clarification there, which is I can see that well, many years ago I was involved in the Singapore MIT Alliance, and we would have a live audience in the lecture hall, and in Singapore simultaneously we would have a lecture hall filled with students from the Singaporean universities. And in fact, it went very well, but it was very high touch, very expensive technology, very, very time consuming. Of course, the technology was new at the time. But I want to emphasize that what I'm proposing here, and that's why I guess maybe I'm saying it's not hybrid, is that the lectures would all be synchronous Zoom lectures to all the students, be they online or on campus. And so the actual core of the course would be homogeneous across all students. And so I really only see the distinction between, in that sense, to me, it is not hybrid, right? I mean, it would be equivalent to the fact that maybe a student happened to have at home an expensive thermocouple system, and they would use that instead of the transducers that we provide. As it was, I should mention, Dan, that when we did 251 last fall, when Max took the course, a lot of students elected to use their laboratory resources, not a lot, I would say a handful, laboratory, which I allowed, right? And so that in some sense was already hybrid, but I found very little distinction when I was looking at the projects between the students that had used the provided material and those that found other sources. So I think that I can see that having two distinct groups and trying to manage both of them could lead to a degradation in quality for everybody. But what I'm proposing is that there's really a very homogeneous core to the presentation, and it's just these sort of optional elective parts where students can choose to complement each other. But I also think in the hybrid model, if you don't make an effort to make sure that in fact there is not a better experience for one group of students than the other, that could be very poor in terms of both the spirit of the students that are not in the, if you like, preferred group. But so I would like to see that data and really see the definition of hybrid before I would judge that you can't do things in a perhaps complementary way. And I should point out that students themselves vote for hybrid experiences. I give classes where I never see students in lecture, right?
Yeah.
Right, and so that there is a hybrid experience, right?
Yeah.
And I see some classes where some students show up for every office hour and others don't. So I think a system which allows options that may depend on location is different. The other point is that some experiments will work for some students in some locations and others not. We had this past semester, we had students all over the world, right? And so different experiments would occur just based on natural location. But I would like to see more about that data to make sure that I'm not repeating hybrid errors of the past, but maybe trying to propose a different model that's, say, flexible rather than hybrid.
I'm encouraged by your approach. I think it'll
I thought
work.
you were going to say, I'm encouraged by your naive optimism, as I thought how that sentence was going to end.
No, not at all. Not at all. I have a hand up. I want to recognize Adel El-Shabasi.
Excuse me, let me explain about the hybrid. We can use the lecture for the student, all the student can be given online.
Yes.
And it's okay. And this is equally for all the students. And then we can use the lab or the tutorial or something like this on the campus. So all the students take the lecture online and all the students take the lab on campus. So it is fair now. There is no distinction between, there is no difference between some group take online and some group take on campus. No, I mean that we offer the course through online lecture and on campus lab and tutorial.
Oh, I see. So in any given semester, a student would be taking the online class and then would be going in to do the experiments on campus.
Yes, that's what I mean.
Yeah, well, that to me, I guess hybrid is right, but that to me would not seem to have any educational dangers in some sense. It's just it seems to me that it's, again, as long as the two groups, there are no two groups in your case, it's just two locations, and that would seem to work very effectively. No, the reason I think that we cannot do that at MIT is that one of the issues is population density on the campus, and so the question is whether the students would even be in the dorms, and if they were in the dorms, who would have access to the laboratories and with what frequency. And so, it depends entirely on the real estate situation, whether or not that kind of model would work or not. But I agree, I see that as a net plus, not a negative.
Okay, thank you.
So I have a question for you, Dr. Tamer, following up on your interesting presentation on the virtual experiments of different types. So have you or has Ain Shams been part of an experiment to do assessment of the effectiveness of the different models you presented? Or has there been any, I know that you did some of this work as part of experiment with the EU, as I understood it. Has there been sort of a more broad effort to assess the different models of engaging the students in experimental activities, but not necessarily in person?
Yes, we did. As part of this project, we did some assessment, but it was mostly based on student feedback. So we had organized questionnaires for every student who take this and ask him about what he thinks. Actually, most of the students, of course, they had lots of feedback about the usability, the problems, and we learned a lot from the beginning because they were not as robust as they are now. So we learned a lot from the students how to make them better and how to make them more real and more user-friendly. We also learned a lot from them over the years how to make things self-explanatory. So when he goes on to the experiment, he knows there are some enough hints for him to tell him what to do. And also with error messages, if he does something wrong, as I said, most of the time we allow him to do the wrong thing, but if he wants to go to the second step, then he cannot, and then it tells him you did that wrong, so you need to go back and fix it. But most of the students, we got very positive feedback from students, and they thought that it is fun to do this. So these students of these days are used to play with video games and tablets and computers. So anything engaging this new communication model was very welcome by students. And as I said, all these experiments, what they also were happy about is the availability. That they can actually, go on and repeat and do it again and again. So the availability was something very positive. Again, as I explained in the beginning, these are the intended learning outcomes out of this experiment is to teach them the procedures of doing things. And also, if there is some calculations, yes, they do it. And of course, they cover a lot all the, for example, these signal analysis techniques. You do this in MATLAB, you do this over the computer. So this is something that they do anyway on a computer. By the way, I forgot to mention that for the signal analysis, it is connected to the microphone of their laptop or the speaker, so they can inject, they can whistle or play some music or do something, and then they analyze this. So yeah, it was quite interactive, but still they do not replace any practical skills that the student acquire in a lab. Of course, this is something, when you are in a lab and you take care of the safety measures to hold things, for instance, the micrometer experiment, holding the micrometer and adjusting it is a skill that the student don't get here. What they get is the measurement, because the reading itself is a bit complicated. It's not very straightforward. But how to hold the micrometer, that's something else that, of course, we miss here.
Let me recognize Ahmed Hamed.
Okay, thank you, Dan. We have some students live in close areas in Mansoura University. Is it possible to think about allowing them to conduct practical experiments in small groups, taking into account, of course, the precautionary measures? Because our students do something like that before the pandemic. Can we continue in this experience in this period?
I just want to make sure I understood. So the idea is that these are students that would be working together in laboratories, not virtually, but together physically in laboratories conducting experiments. Was that the question?
No, they conduct the experiments or actually the mini project, but at home. They did the project at home.
Yeah. Oh, so your question was: is that feasible? Was that the question? Just.
Yes. Is that feasible to do something like that in this period?
I should say I hope so. That's what I'm going to attempt. So but I should mention that even last year, when we taught the heat transfer subject, the majority of the experiments were done at home. I mean, I showed you one picture of the tub humidifier that Max considered in one of his project case studies. I believe, Max, that humidifier was in your dorm room. Is that right?
Okay.
Yes, it was.
Very good.
Yeah, so most of the experiments, some students ran across the bridge and then took temperature measurements and they were outside. Other ones or carried pasta through the night. Other people had setups in their dorm rooms. A few people were using kitchens. Some people used a laboratory. They happened to have access to it at MIT. But again, I saw no real difference between those. So I think the key is that 251, my particular subject, is not a course about med per se. They have other courses on that. And so what we need is something that is going to be reasonably accurate and robust in a not particularly pristine environment. And trends and, rough accuracy are sufficient for our purposes. The answer might be different if you're doing experiments that require very detailed setups and an extremely controlled environment. I tend to try to emphasize topics in 251 because of the everyday life that methods that are robust, right? In the sense that the methods do not require huge amounts of input to be able to pursue. So the answer might be different if you're looking at a different discipline and if you're looking at a different level of precision. But certainly doing experiments at home, and Dan, I think there's other examples of that from this past spring, right? Where I believe it has been successful. Dan, do you have any?
We're going to feature that next week. Ian Hunter.
got
Yes.
I think we're getting close to the end of our time period. And I want to thank you all for your active participation. And I also wanted to mention that the person who usually helps us each week with coordination, that's Ariel Ackerman, this week has given birth to a nice, healthy, beautiful 9-pound boy. So we're all happy for her.
Congratulations.
So please do register for the subsequent sessions, particularly next week. We're going to be having a presentation about experiments that are physical experiments, but they're conducted remotely with equipment that's been designed from the bioinstrumentation lab at MIT. So we're looking forward to that, and I look forward to seeing you again next week.
Thank you, Professor Fry. Thank you, Professor Tony. Thank you very much, Max, also for your participation today. And thanks to everyone for attending.